Okay, thank you, Jamie. Our next speaker is Rob Warren from Stellenbosch University in South Africa, and Rob's going to talk on lights on, lights off, clinical evaluation in South Africa, and this is the essay that David Hain mentioned earlier today.
Well, to start off with, I'd really like to thank the organizing committees, both from CPTR and ReSec-TB, for bringing me all this way from South Africa. I don't know whether it's a punishment or not, because it's quite difficult to adapt to the changing time frame. So I'm really going to speak a lot about the lights on and lights off technology and a little bit of how we're moving towards evaluating that, but all of the data is blinded, so it's very difficult to be able to give you any sensitivities and specificities. The talk will really focus on it, give it a little bit of background, and I think we try to set the scene as the problem of drug resistance in South Africa, and then I'll give a short description of the methodology of late PCR, and then we'll look at the assay for looking at XDR, which came up in the discussions earlier when David gave his presentation, and then we'll look at a study that Larry and Barry have been working on in terms of pyrazinamide drug susceptibility testing using this technology. So in South Africa, the recommended diagnostic strategy focuses on using expert as the primary screening tool, high tech, and then we move, once resistance to rifampicin is noted, we move into very low tech, and we do culture-based DST, which, as we've heard, takes an extremely long time. In fact, it's on average in Cape Town or the Western Cape around 2 months. But despite this, the guidelines that were published in 2014 clearly recommend that we have to put patients who've got rifampicin resistance onto MDR treatment within 5 days. So this is the strategy that's being taken at the moment. And clearly this was not the consensus of what I think this meeting feels about, but we heard yesterday one of the comments being that one really needs to know what one's treating. So what is the consequence of doing this? And this is just looking at a pie chart of susceptibility in terms of the proportion of patients who are susceptible to 5 drugs. In other words, they'd be really getting a good regimen, and it's only 27% of the patients in the Western Cape. Around 47% of the patients are getting 3 or less drugs. And we really know that this is a problem, and it has the potential of amplifying resistance. And I think South Africa is becoming one of the world champions when it comes to XDR-TB. And this is one of the factors that's probably driving this epidemic. So we really need new technology. And we've heard about next-gen sequencing. Clearly that's going to be the gold standard, but I don't see, as was also mentioned today, that can be rolled out into the whole of Africa and in most parts of Asia. So we need technologies that are as informative, and one of them is late PCR, which is linear amplification after the exponential. So what happens, very briefly, for those of you who haven't heard this before, is one does a standard PCR with very cleverly designed primers in different ratios that in the beginning of the amplification process allows us to generate a lot of double-stranded DNA. And then one of the primers runs out, and what happens is that amplification turns from exponential into linear, and we get lots and lots of single-stranded DNA, which is the advantage because now that single-stranded DNA can interact and hybridize to probes, and we can then look at the way that those probes now interact with this amplified DNA in a way through a temperature space, and looking at the stability of which those probes bind to that DNA. So here's an example, just a graphic example. If we have the single-stranded piece of DNA, we have a probe with a fluorescent marker and a quencher, and then we have an off probe, and these can bind, the on probe can bind to the single strand, and the off probe can also bind, and then when one now melts this hybrid, one sees that one gets a particular fluorescence curve, which is indicative of a particular DNA sequence underlying those two probes. And if there is a mutation, the probes would hybridize, but they would hybridize with different stabilities, which would change this fluorescence signature. And that fluorescence signature will be very characteristic of the particular mutation that is underlying one of those probes. So what we have been trying to do is to be able to develop this assay that allows us to look at different gene targets as well as to collect a large bank of isolates that we can then evaluate the methodology on. And so we have here cultured DNA samples, and they're all blinded at the moment. This 1,000 isolates is being blinded, and we have a reference set, which is a training set that we can use to try to understand the relationship between the fluorescent signature and the particular mutation. And then we've been collecting a large bank of clinical isolates where we have residual sputum, we have a genolyze extract that comes from the line probe assays, as well as having the culture. And all of these have been banked together with the associated diagnostic data. So the design of the study, of the assay, I should say, is based on the fluorotype MTBDR assay, which was presented by David Hain earlier on his new assay, which in one color looks at isoniazid resistance through the INHA promoter and CAG, as well as through rifampicin resistance through RPOB, RRDR, and then there's an internal control, and he also has an amplification control. We've moved the amplification control into a slightly different color. We've included the ICE gene as well as the RRS for aminoglycosides and 2 genes for the fluoroquinolones. So this is what you see, and these are in the different colors. And one can see here is the INHA promoter, the CAG, RPOB, all giving particular signatures. This is for H37. There's the internal control. And so it goes on for the aminoglycosides. We get a very characteristic pattern for JAR B and for JAR A. So here's a bit of an expanded picture showing the fluorescent signature. And if we now superimpose clinical isolates that are wild type onto this, one can quite clearly see that they're very much a consistent pattern that is definitive of the sequence being highly conserved in those regions. And this is just an example of 50 isolates all overlaid. If we look at strains with mutations in RPOB, for example, at the position 526, one can quite clearly see how this RPOB fluorescent signature moves according to the different mutations, which I think is actually a really important component rather than just having an assay that gives us R or S. Why do I say that? Well, if one looks at the MICs for rifampicin at different positions in RPOB, there are certain mutations that are not conferring an MIC above the critical concentration. And I think that's quite important, as it may impact on how we would want to treat particular patients with particular mutations. I know there are many more, but they also go slightly above the CC. Here we can see, by superimposing numerous clinical isolates that have the same signature on top of the standard H37, one can see that we have strains with a particular mutation in the INHA promoter. They have a wild-type CAG and a particular characteristic RPOB mutation, indicative of a particular clone or spread of strain in the community. Here's another example. This is a classic strain. It comes from the Eastern Cape. We described it as a TDR strain a few years back, has a 516 RPOB mutation, has a CAG mutation, and a very unique INHA promoter mutation. And clearly, these strains, as we indicated in the group that we've been studying, out of 852, there are 45 examples of this particular strain circulating in the Western Moving on to the aminoglycosides, one can quite clearly see that if there is a mutation, which is 1401 A to G mutation commonly seen in our isolates conferring aminoglycoside resistance, that we get a shift in the signature, which can be relatively easily recognized visually. In terms of the ICE promoter, found very rare in South Africa. There are a few examples, and these examples were picked because we'd done whole genome sequencing and had the data, and one can see that different mutations confer a slight change in the signatures, which are, again, relatively easy to recognize and thereby score the presence or absence of these mutations. We do not see mutations in JRB at all in South Africa so far, even in all of our isolates that have been sequenced. We sequence mainly drug-resistant isolates, so that is not a particularly strong target for conferring fluoroquinolone resistance in our particular context. Looking at the JRA mutations, there are numerous ones found in our collections, and I think what's quite clearly seen, there's quite a bit of noise in this particular channel, but one can quite clearly see that each mutation gives a different signature, allowing us to be able to discern which mutations are conferring resistance, which will have an impact on the level of fluoroquinolone resistance, particularly in terms of moxifloxacin. These are the mutations that can be differentiated, and I won't go through the list. I think it's important, though, to highlight that there are some that we are not at the moment able to differentiate, those base pair differences. There's the 3 in RPAB, 2 in JRA at the moment. But when you've got multiple mutations, you can obviously detect them. Now I'm going to change gears slightly and look at the pyrazinamide assay. The idea of this assay was not to be able to go and discern all those different mutations. That would be really a tall order to achieve, and one can do that by sequencing. We wanted a methodology that was really quick and simple that can tell us wild type, so that you can really target those patients with definitively by using a pyrazinamide in their regimens. But what I wanted to show in this particular study, that has just been submitted by one of my PhD students, just showing where do we find pyrazinamide resistance in our clinical isolates in South Africa. So in pan-susceptible isolates, we do not find them at all. Or isoniazid and rifampicin susceptible isolates, there's no pyrazinamide observed. When we go to isoniazid mono, it's extremely rare into percentage. Rifampicin, it starts to rise, so that we see polyresistance here. As we go into the MDR, it becomes a very important component, and we're not taking this into account at all in terms of the treatment regimens that are actually being used. We are assuming, I think, in South Africa that pyrazinamide in MDR is going to be an effective drug. In XDR, clearly, it's not useful at all. So the assay is also slightly differently designed. It has a large number of probes, on probes and off probes. In fact, there's 17 pairs scattered across the gene, and they're not all lined up next to each other for each color. They are scattered so that they will be seen as their melt profiles will be, how can I say, within a particular color, they will be looking at different regions of the gene, not trying to look at just one region in one color, as we did with the other assays. Wrong direction. Is that right? No, I've got it in twice, sorry. Here's we see looking at them in 3 colors, so I'm going to give 3 slides. Here we can see some examples of wild type, very nicely superimposing on top of each other in the quasar channel, cal red channel, again superimposing very neatly on top of each other, easy to recognize, and the same with cal orange. If we have mutations, here's a particular insertion at position 173, one can see dyslexic. We can see a clear change in the signature, implying that there's a mutation. So one would then be able to score that as having a mutation, indicative of resistance. Whereas the other channels are showing that there are no mutations. And I've got two examples of this. Here's another one, another strain with a particular mutation at position 202, and one can see there's clearly the change in the fluorescence signature indicative of presence of a mutation. So we would score these isolates as being resistant, whereas all the ones that have a signature mimicking the wild type would be indicative of susceptibility. So far, 650 isolates have been analyzed, of which 240 are wild type, 414 have PNCA polymorphisms. The correlation between Sanger sequencing and late PCR, well, 234 out of 240 concurred, which I think is really pretty good for this complex gene. 6 of them are discordant. If we look at the mutation, those with mutations, there's a very good concordance, 391 out of 414 identified within that group 180 different polymorphisms. So the assay, I think, is doing really well. The sensitivity and specificity are right up there where we would be, I think, that they have utility, particularly in identifying patients who would benefit from using pyrazinamide. Then I'd just like to thank all the collaborators in the group at Stellenbosch, and Larry Wang and John Rice at Brandis, Barry Kreisworth and Salvatore, who've done most of this work, and then, of course, David Hain and National Health Laboratory Service in South Africa, and the NIH for funding. Thank you very much.
Questions for Rob?
Yeah, heteroresistance is always a difficult animal to attack. We don't. We haven't done a clear study where we've titrated a wild type and a mutant to look at that so far. No. But it's an important issue, and I think in South Africa, particularly patients, if we're looking at fluoroquinolone resistance, that emergence of fluoroquinolone resistance needs to be detected early, and heteroresistance needs to then be an issue that an assay can address rapidly and early on, that we don't have to wait until there's, the mutations are present in a sufficient amount. Yeah.
Yes, I have one question here.
Yeah.
So in your probe design, how long are your probes?
I'm going to hand you over to Larry. Do you know them by heart?
Depending on the test, probes tend to be about... All right, the probes tend to be about 25 nucleotides long for the XDR assay that Rob was talking about, but for the pyrazinamide assay, I have to get this right, the on probes are 25 nucleotides, and the off probes are about 15 nucleotides long.
So
In general, the off probes are present at threefold higher concentration than the on probes, so as to guarantee that regardless of the concentration of the product that you've generated, the off probe will always be sitting down next to an on probe.
Right, then you only have 17 probes to cover the entire gene?
34 probes.
Yeah, it's 17 pairs, I said.
Oh, okay.
17
Sorry.
pairs,
Okay.
yeah.
Thank you.
And just to comment on the previous question about mixtures, we did a small study for the RPOB gene, and We can see down to about 10%.
Rob, I was surprised that you don't see any variations in GIB, because we know that there are phylogenetic polymorphisms in there, and because they are used for discriminating TB complex. So you actually should see variations just because of phylogenetic reasons, similarly to some of the other genes.
But then we're not incorporating all of the complex members here. This is only tuberculosis. Well, we see none.
So, Rob, I have one question. So, given what you know about your MDR strains that are 40% pyrazinamide resistant, if you were in charge, what would you suggest they do in South Africa in terms of, detection as well as treatment?
Well, I think in South Africa we need to move to tools that can give us an answer quickly. And I think there are tools out there. The SL line probe assay is out there. It could be applied. It's been out there for a long time. It's still not used. So we're in denial in some way. And I think that we really do need to implement an assay like that or an assay like this, but this needs obviously a lot more development and evaluation. I think that if we could do that, and we're actually planning a study to do that now, to see how quickly we can get patients onto treatment. And we're hoping we'll be able to do that in a week's time, which is the target, but with the extra data. In terms of, one would like to be able to incorporate additional and strengthen the regimen that is currently being used. It's really difficult to say which drug we want to put in. I think bedaquiline would be great, but we definitely need a strengthened regimen, particularly in the Western Cape, where we have this chronic MDR epidemic that's really matured from being sensu stricto MDR to being MDR plus. And I think that's something that we really need to take into account. And I think the program needs to take into account as well that our MDRs are not just resistant to isoniazid and ref. And that's not really been taken into account.
Thank you. Any further questions? Okay, thank you, Rob.